Okay, so I have two examples for you today. You need to take notes on this. The first one just answers an important question. And the question is, can we write a 3D vector in polar form? It's a really good question. So that will address that. And then the second example has nothing to do with that at all. It just shows us the power of vectors. Okay? Also, you'll notice I sent you a third worksheet on Friday night. Okay? Does anybody need a hard copy of that? Okay, so the first question is, let's just run right the question. Can we write a 3D vector in polar form? That's the question of the day. Okay, let's just draw a quick picture of the 2D situation. So remember, this is a review of 2 dimensions. Okay. In 2D, we have a vector, and we describe it 4 different ways, actually. So this is A and B, and this is the vector. And we can write this as vector V is A comma B. We use these brackets, right? And this just basically tells you what the run is and what the rise is. And this has a great name. These are the components here. Remember? So this is called component form. Isn't that great? And it's rectangular because it tells you how to move left, right, up, down, that sort of thing. So this is called rectangular component form. Okay. And then if you decide to use theta and magnitude instead, that's the angle and the magnitude instead, you could just simply rewrite this as, instead of A, you could write magnitude V cosine theta, and instead of B, you could write magnitude V sine theta. But most people actually bring the V outside, and they write it like this. Although I've seen people leave it inside too. So these are still components. They're still the run and the rise, but it's a polar form. So this is polar component form. And I don't care if you leave the V outside or put the V inside. That doesn't matter too much. Okay, then we have the I hat and J hat thing. But that's not really new. It's just a different way of writing this. So instead of A comma B in brackets, we can write A I hat comma B, I'm sorry, not comma, but rather plus B J hat. The plus actually does not mean addition. It's so weird, but that plus is like a comma, is really what it is. It separates this and this. It's kind of like if you said, if somebody verbally said carbon monoxide is carbon plus oxygen. Is it really carbon plus oxygen? It's not plus, you don't add elements, but you can say it's carbon and oxygen, right? So this is sort of the same idea. It's A and B. Weird that they're using a plus here. I don't know whose fault this is, but it looks like a scientist thing to me. I'm not sure. It's just notation, right? You can use A comma B if you want. All right. Anyway, it's called rectangular because you see the A and the B, right? And it's unit vector form and then the last one is where you take this and write it as magnitude V cosine theta I hat plus magnitude V sine theta j hat. And this, of course, would have the name polar unit vector form. Polar unit vector form. Okay, so I give you 4 forms because there's at least 4 forms, and different textbooks use different forms, and you don't want to go into Ms. Fusco's class or into your college class, and the teacher's in this, and you're like, I have no idea what that means. You'll know, oh, that means this, and this means that, and it's all the same thing, right? So when we go into 3-dimensional vectors, right? Things like magnitude still make sense, right? But what does theta mean anymore? Like, even the word slope in 3D doesn't mean anything at all, right? Slope literally means rise over run. How do you measure the rise over run for this stick right here? Like, if I just point this stick like that, what's rise over run? What's delta y over delta x? Well, where's the y-axis? The y-axis could be pointing that way. Or that way. You see what I'm saying? So some words lose meaning when you go into 3D. Like, the word slope literally means nothing at all in 3D. It doesn't even mean anything. Okay? All right, so because of that, we have to kind of redefine things. Maybe we don't need a polar form, right? Like, for example, maybe you might think we don't need a polar form. Let's say you just want to draw the vector 2, 3, 4, right? You want to draw the vector 2, 3, 4. So I taught you kind of how to do that. You draw an x-axis this way, right? Draw a y-axis maybe that way. Z-axis goes up. And you just go this way 2, and this way 3, and this way 4. And I like to draw little breadcrumbs. Dot, 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 dot. Up 2, 3, 4. You remember doing that. Here's your vector, big fat red vector. Why do we need a polar form? Who cares? Well, if you were trying, let's say that this was an asteroid coming from outer space, and you need to blow it up with a missile, I don't think you should program your missile launcher using 2, 3, 4. I highly doubt the missile can follow that green path. See my point? How are you going to get the missile to follow the green path? 90-degree turns in the sky? I don't think so. There's infinite acceleration at these two corners. You can't do that. It's impossible to turn something 90 degrees in midair without stopping. It's impossible. Okay, so that's not going to happen. So we definitely need polar. That's what I'm trying to tell you. We need polar. If you want to shoot the asteroid with the missile, you need to tell it how far to shoot. You need to tell it which way to shoot. And it's a straight shot, not a curved path or rectangular path of any kind, right? Okay, so the length here is simple enough. It's just root 29. You can tell the missile launcher, hey, shoot this thing, rad 29. And if you just told it that, though, then it would just shoot the missile any old way, rad 29 miles or whatever, right? Who knows if it's going to hit the asteroid? Okay, so you can't just have a number. Magnitude's not enough. So what we need to do is define a new system. What did you want to suggest?
Well, if you're doing, don't you need two angles on two circular planes?
Yes, we actually need 2 angles at least, okay, to tell the missile launcher which way to shoot it. It turns out we actually use 3 here in vectors. In what we call spherical coordinates and cylindrical coordinates, we actually use 1 distance and 2 angles. Or in cylindrical coordinates, we use 2 distances and 1 angle. You need 3 different things to describe a point in space, whether it's x, y, and z, r, theta, and phi, r, z, and theta. You'll see all those next year in my BC class. But for the vector world, we actually use 4 things. We use the root 29, and we also use these 3 angles. Watch close. This angle is called alpha. It measures between the red vector and the x-axis. And this angle, theta, it measures between the red vector and the y-axis. And we need gamma. Gamma measures between the z-axis and the red vector. So we're going to try to describe this vector by measuring how long it is and how far it is angle-wise from each of the 3 axes. That way there's no question where that vector's at. Okay, the alpha, the beta, the gamma, these are called the directional angles, or the direction angles. That's a great name for them, isn't it? What a great name. They are all acute angles, okay, in my picture. But you could probably imagine that if this thing was firing off to the left a bit, that the alpha might actually be more than 90. Okay? So the question is just how do you find them? And that actually is not a new question because we've actually been talking about angles between things already. So here's an old friendly formula for you. Cosine theta is vector dot vector over magnitude vector times magnitude vector. Raise your hand if you remember this formula. You've been using it on two worksheets at least. You've used this several times. Okay, this is the idea. Now I just need vectors. Okay, so watch close. This is the tricky part. There's a tiny vector on the x direction, right here. His name is I hat. Everybody say hello, I hat. The angle between the red vector v and I hat can also be found using this formula that I just wrote. But the formula would look like this. Cosine of alpha equals v dot I hat over magnitude of v times magnitude of I hat. I'm just applying this same idea to the red vector and the x-axis. For x-axis, I'm going to call that I hat. Same thing as x-axis, right? It's a unit vector anyway. Yes, and what is the magnitude of I hat? How long is it? The magnitude's 1, right? It's a unit vector, right? So this length is 1. And let's not use any numbers yet. Let's just, for the sake of argument, say that u, or v, is the vector ABC. What's going to happen if I do ABC dotted with 1, 0, 0? What are you going to get if you take ABC and you dot it with 1, 0, 0? A. Yeah, because you're going to get A times 1 and B times 0 and C times 0, so you're going to add them all up. A plus 0 plus 0. So this is just going to give us A over magnitude of V. Okay, so here is our first formula of the day. The first directional angle can be found by using this formula. Okay, now today's a minimum day, so I'm not going to rederive everything for the other two formulas, but know this, the next time I want to find an angle between the red vector and the y-axis, I will use j hat. Okay? And I will just put a j here, and when I put a j here, that's going to make this 0, 1, 0, and this is going to be b over magnitude v, you see. So I'm not going to get too carried away with derivations today, but just know that cosine beta is b over magnitude v. And you guessed it, cosine gamma is c over magnitude v. We would actually try to find the dot product of the red vector and k hat. K hat, which hopefully you looked up last night, is 0, 0, 1. Okay, so these are your three direction angles, or these are actually called the directional cosines. And then we could get the three angles from them. So I think it would be cool to find the directional angles for the vector 2, 3, 4. My favorite 3D vector. Okay, so my favorite 3D vector. Let's find the direction angles. Okay, so for example, find the direction angles for 2, 3, and 4. Okay? Then write the vector in terms of its direction angles. This is our fancy way of saying use polar form and write the vector. So this is like a polar form of 2, 3, 4. Okay, this is very, very easy. Okay? To get your alpha, you're going to go cos alpha equals 2 over rad 29. To get the beta, you're going to go cosine beta is 3 over root 29. Then it'll be cosine gamma is 4 over root 29. See? That's not hard. Let's get the calculator going. Okay, so for the first one, I get alpha is about 68.199 degrees. For the second one, I get beta is about 56.145 degrees. Make sure your calculator's in the degrees mode, right? And for gamma, 42.031 degrees. What are those things? Those are just the angles between the x-axis, the y-axis, and the z-axis. Okay, so that's the answer for their first question they asked us. How do you write this vector 2, 3, 4 in sort of a polar type form? You slap a rad 29 in front. Watch close. You write cosine 68.199. Cosine 56.145. Cosine 42.031. You might say, Mr. Shore, why are you using cosine all three times? I thought in polar form we do cos theta sine theta. We are not in that world anymore. We're not in the world of theta anymore. We're off the plane. So it turns out that they decided to go ahead and use cosine all three times for this. There's no sines at all.
You could make a sine though.
You could do sine, for example, you could call this, you could find the complementary angle and write this as sine 40, or sine 33.855. Okay? So what's going on is in the world of two dimensions, we always insisted on measuring with respect to the x-axis. We would never measure with respect to the y-axis. But if we had, we would have had absolute value v sine alpha, cos alpha, cos beta. Okay, so we just never did that. We always tried to just stick to one theta, you know. And here we're using all three. So don't stress out too much. Just know that you're supposed to use cosine all three times. And if you don't believe me, I will show you that this makes perfect sense. Here's your check. You can see from up above that this is 2 over root 29, 3 over root 29, and 4 over root 29. And what do you get if you distribute root 29 into this vector? What do you get? 2, 3, 4. Yeah, I mean, look at it. It's going to give you 2, 3, 4 if you distribute that, right? So we now have a way to program the missile launcher. We will tell the missile launcher not 2, 3, 4, but rather root 29, cos 68.199, cos 56.145, cos 42.031, and the missile will hit its asteroid. Okay? So I showed you the need for it, showed you the method for it. It's not new, it's just an application of our famous angle between vectors formula. Second question today is find the area of a parallelogram. Okay? This has nothing to do with example 1. So find the area of the parallelogram whose vertices are and I'm choosing this problem straight out of the textbook. Okay? Because it's very difficult to make these up without messing them up. So the vertices are 1, 1, 2, 1, 2, 3, negative 2, 3, 0, and negative 2, 4, 1. Now I'm going to draw this real quick. You don't really have to, but I'm going to draw it just to help you understand the question. This is a simple problem in a way. It's just asking for the area of a parallelogram, but it's a complicated problem in a way because I don't think we can use traditional geometry for this very easily at all. Okay, so I'm just going to plot these points. Where's 1, 1, 2? Let's go ahead and mark off our x-axis 1, 2, 3, 4 at least. You can do more if you like. Maybe a couple negatives there. I don't think we need any negative z's at all. Look at the instructions. There's no negative z's anywhere. Okay, so my first point is 1, 1, 2. That's this way 1, straight up 2. So my first point is right there. P1. Second point is 1, 2, 3. A little higher up the page. That's point P2. Negative 2, 3, 0. That's actually on the plane. And negative 2, 4, 1. Probably right about here. Now you don't have to draw this, okay? The only reason I'm drawing is to show you that basically the name of this parallelogram is not what you might have thought. You might have thought that the name of the parallelogram would be P1, P2, P3, P4. That's not true. The name of this parallelogram is P1, P2, P4, P3. You'll notice that the arrangement of the letters is not quite the order you'd expect. It goes point 1, point 2, point 4, point 3. P1, P4 is not a side of the parallelogram. Okay? All right. So what I'm planning to do, I'll finish this video, but what I'm planning to do is just find the cross product of the P1, P2, and the P3, P1 vector, and I'm just going to get this long, long red arrow pointing that way, and the length of that thing will be the area of this here. So you can watch the rest of this video. I was going to post it this evening. But your third worksheet does have a problem like this, so you can just watch it. It'll take about 5 minutes to watch, and then about 5 or 10 minutes to do the problem. It's due tomorrow, and it's on the printer for those who ask for a hard copy.
Wait, and do we have a group quiz tomorrow?
Yeah, group quiz is tomorrow.
Okay. And this covers all from 8.1
8.1 to 8.4.
Okay.
So my strategy is to find the cross product between the following purple vectors. P1, P2, and P1, P3. We'll find the cross product, and then I'm going to take the magnitude.
We had, like, we didn't have, Doug was so down and then he was like,
Okay, but first I need to have the vectors in place.
oh, they're so bad.
Okay, so how do you find a vector here? Well, P1, P2 has its tail at P1, tail, and has its head at P2. So you would want to construct the vector P1, P2 by basically doing head minus tail. Head minus tail.
Oh, it
Head
wells?
minus tail.
Oh, it wells?
And you're going to do that 3 times. Okay. So let's look at P1. I'll circle them up here. P1 and P2. This is the head. This is the tail. Okay, so we're going to do head minus tail 3 times. Head minus tail gives me 0, 1, and 1. Let's do the same thing with P1 and P3. Be careful here. P3 is actually the head. Okay? But we are going to do head minus tail. So negative 2 minus 1, 3 minus 1, 0 minus 2. So this is always head minus tail for every one of these 6 calculations. Okay, and then to set up a cross product, you're going to do this. I, J, K. Put in the first vector here, second vector here. And we start off by doing I hat. 1 times negative 2 minus 1 times 2. Mandatory minus there. Then next is J hat. And we have 0 times negative 2 minus 1 times negative 3. And then back to plus. And then 0 times 2 minus 1 times negative 3. And this gives you 3 components. We have negative 4 I hat. Looks like we have negative 2, or basically we have negative 3 j hat, and we got 3 k hat. And this is our vector, the cross product. If we find the magnitude, 16 plus 9 plus 9, that's root 34. That is the area of that parallelogram, not just the length. So I'm just reminding you that the length of the red is the area in red.